The global transition to electric vehicles currently rests on a single, heavily constrained foundation. To build the batteries that power this revolution, the world is pulling millions of tons of lithium out of the ground. The supply of this raw material is highly concentrated. A few select countries control the vast majority of active reserves, creating severe bottlenecks in the global supply chain. Beyond the geographic constraints, the metal is expensive to refine and carries inherent physical risks. Under certain conditions, lithium batteries are prone to thermal runaway, a chemical chain reaction that leads to uncontrollable fires. Scaling global energy storage using a single, geographically limited and volatile element is structurally unstable. To sustain the energy transition without creating new monopolies, an alternative chemistry is required. Sodium sits directly beneath lithium on the periodic table, meaning it can facilitate a similar electrochemical reaction. But unlike lithium, sodium can be extracted from inexhaustible sources, like seawater and common rock salt. Sodium makes up 2.6% of the Earth's crust, completely dwarfing lithium at 0.005%. But because sodium ions are larger and heavier, they store less energy by volume, resulting in a heavier battery for the same power output. That extra weight yields a 30% reduction in manufacturing costs. With aluminum current collectors, these cells can be safely discharged to 0 volts. They also operate reliably in freezing environments where lithium cells fail. The laboratory physics are largely settled. The deciding factor for the next generation of energy storage is industrial execution. Whoever can manufacture these cells at a global scale first will capture the market. Chinese manufacturers have already moved past the prototype phase. In 2025, they produced gigawatt-hours of commercial capacity, accounting for most global sodium-ion shipments. Companies like CATL are actively deploying these units. Their new Naxtra sodium-ion brand recently passed national certification, verifying its ability to reach an 80% charge in just 15 minutes. This diagram illustrates how Chinese automakers are mitigating sodium's weight penalty. By physically integrating lithium and sodium cells into a single hybrid battery pack, they balance cost, cold weather reliability, and driving range. While competitors in other regions continue to test pilot lines, China is currently locking down the material supply chains and setting the global manufacturing standards. Sodium is not a direct replacement for lithium in every sector. High-end, long-range electric vehicles will continue to require lithium's superior energy density. Instead, the market is fracturing based on utility. In massive stationary grid storage systems, physical weight is largely irrelevant. For utilities balancing solar and wind loads, the cost per kilowatt-hour is the dominant metric, making cheap sodium cells the optimal choice. The other primary application is entry-level mobility. Two-wheelers, scooters, and low-speed urban vehicles are highly price-sensitive, and sodium batteries keep these production costs aggressively low. This specific market split dictates the future of global energy. The nation that manufactures the cheapest grid storage and entry-level transit batteries will control the infrastructure of the developing world. India has recognized this strategic vulnerability. Through its new energy subsidiary, Reliance Industries acquired the UK-based sodium-ion technology company Faradion for £100 million. By absorbing proven sodium chemistry, Reliance aims to bypass the constrained lithium market entirely, funneling this technology into massive gigacomplexes currently under construction in Jamnagar. They are not acting alone. A wider domestic ecosystem is forming, with local engineering firms like KPIT recently launching their own proprietary sodium-ion cell technologies. However, acquiring patents and completing lab tests is only the first step. India is currently tasked with translating these prototypes into commercial volume, facing a stark production gap against an already entrenched competitor. In deep tech hardware, the true protective moat is logistics. Having the best chemistry means little without the industrial capacity to mass produce it efficiently. This diagram illustrates the disparity in industrial readiness. China operates a tightly looped, self-contained supply chain, moving raw materials to finished battery packs with minimal friction. India's current battery production network remains highly fragmented and disconnected by comparison. To bridge this gap, the Indian government introduced a production-linked incentive scheme allocating over 18,000 crores to stimulate large-scale domestic cell manufacturing. Yet, while the policy is designed to be chemistry agnostic, the majority of this capital is flowing towards safe, established lithium-ion projects. Domestic producers are hesitant to risk billions on scaling a newer commercial chemistry. Subsidies cannot force innovation. State capital only works if the private sector is willing to absorb the operational risks of bringing a new technology to the factory floor. The global sodium-ion market is in its infancy. Because commercialization has just begun, the window for late entrants to secure market share remains open. India possesses a unique structural advantage. Its enormous domestic demand for two-wheelers, three-wheelers, and low-cost transit provides the exact massive consumer base required to test and scale sodium batteries locally. Energy storage is heading toward one of three outcomes. Sodium will remain a low-volume niche, it will scale alongside lithium as a global co-dominant standard, or Chinese manufacturers will establish an absolute monopoly over it. Time is the critical variable. If domestic industries delay the leap from laboratory research to gigascale production, they will not secure their energy independence. They will simply trade a reliance on imported lithium for a reliance on imported sodium.